Okay, what if I told you that you could send a secret that was physically impossible to steal without getting caught? I'm not talking just hard to steal, but literally impossible according to the fundamental laws of physics. Well, that's not science fiction, my friends. It's the wild and powerful world of quantum cryptography, and today we're going to break down exactly how it works.
You know, this question right here is at the very heart of our entire digital life. Every single time you send an email, buy something online, you're trying to solve this exact problem. How do you share a secret when you have to assume that someone, somewhere, is listening in?
So, let's frame this like a classic spy movie. You need to get your partner a secret key to decode all your future messages. The catch? You can't meet up, and you know for a fact the enemy is monitoring every single communication line. How in the world do you get that key across without them just snatching a copy?
Let's meet our agents. In the world of cryptography, we always call the sender Alice and the receiver Bob. And they have a pretty revolutionary plan to solve this whole dilemma, one that uses the seriously strange and wonderful rules of the quantum realm. Their technique is called quantum key distribution, or QKD for short. They're using a specific recipe called BB84. And notice the goal here. It's not about sending the secret message itself with quantum physics. Nope. It's all about creating a shared key that is provably secure. That's a level of certainty that normal computers and classic encryption can only dream about. So, what's in their high-tech spy kit? First up, single photons. We're talking individual particles of light. They're literally going to send their information one single photon at a time through a quantum channel, which is usually something like a fiber optic cable. And the most important tool? They each have a set of 2 secret decoder bases. This is where the magic happens.
So how do these decoder things work? Honestly, the best way to picture them is like 2 different pairs of polarized sunglasses. One pair, let's call it the rectilinear basis, only lets in light that's perfectly horizontal or vertical. The other pair, the diagonal basis, only sees light that's tilted on a 45-degree angle. So Alice will use one of these to encode a bit, and Bob will use one to try and read it.
And that brings us to the mission itself. Let's walk through how Alice sends her quantum message, photon by photon, straight to Bob.
Now, this whole process is built on pure, unadulterated chance. For every single bit of her potential key, Alice randomly picks a basis, horizontal or diagonal. She sends the photon. On the other end, Bob, who has absolutely no idea what Alice chose, also randomly picks a basis to measure it. They just do this over and over and over again for thousands of photons. All right, so Alice has sent a whole stream of photons, and Bob has measured them all. They each have a long list of results. But here's the problem. Because their choices of bases were completely random, a lot of Bob's measurements are just, they're meaningless static. They need a way to sift the gold from the garbage. This part is just brilliant. They get on a regular, totally open channel, like a phone line that a spy could easily be listening to, and they start comparing notes. But, and this is the key, they only announce the basis they used for each photon. They're just saying, I use the diagonal sunglasses for photon number 1, not the bit for photon number 1 was a 0.
The rule here is super simple. If Bob just happened to use the same sunglasses as Alice for a particular photon, his measurement is guaranteed to be 100% accurate. That's a keeper. But if he used the wrong pair, his result is totally random and useless. So they both agree to just throw that bit away.
Now, just let that sink in for a second. On average, they throw away half of all their data. In any other communication system on the planet, that would be a catastrophic failure. But here, it's the absolute secret to success. It's not a bug, it's a feature. By tossing out all the mismatched guesses, they're left with only the bits they know with physical certainty are completely identical.
What they're left with is called the sifted key. It's a string of bits that Alice and Bob now secretly share. So they have a secret, right? But is it secure? Not quite. They still have one absolutely critical step to perform.
So they've got this shared secret. But now comes the most important part of the whole operation, checking for spies. It's time to introduce our villain, the eavesdropper, who we'll call Eve, because, all this work is for nothing if Eve was secretly listening in the whole time.
This is the million-dollar question, isn't it? I mean, if Eve intercepted the photons, measured them herself, and then just sent them on their way to Bob, how would they ever know? In the normal, classical world, you probably wouldn't. But in the quantum world, spies leave fingerprints. This is the absolute magic of quantum mechanics. See, the very act of measuring a quantum particle,
like one of our photons, can actually disturb it. If Eve intercepts a photon to measure it, she has no idea which basis Alice used, so about half the time she's going to guess wrong, and when she does, she alters the photon before she sends it on to Bob. This creates errors, detectable errors.
So, how do they find Eve's fingerprints? Well, they have to sacrifice a small piece of their new key. Over that same public phone line, they read out a random sample of their bits to each other. They're just checking for mismatches, and if the error rate is higher than what you'd expect from just, normal background noise in the system, then all the alarm bells go off. They know Eve was there. And what do? They burn the key, scrap the whole thing, and start over, completely safe.
But if that error rate is low, they know their key is safe. The coast is clear. They can now move on to the final steps to forge their perfect, unbreakable secret.
First, they use some standard error correction techniques to clean up any of those tiny errors that might have been caused by simple noise on the line. Then, they do this final super clever step called privacy amplification. Think of it like distilling a fine spirit. They use a special function to shrink the key, which basically concentrates its randomness and squeezes out any last little drop of information that Eve might have possibly guessed. What's left is shorter, sure, but it's pure, unadulterated secret. And what do they do with this perfect little key? They use it as the password for a standard rock-solid encryption method like AES. See? All that quantum work was just to securely create and share this one key. Now they can go ahead and encrypt their actual messages and talk with total confidence. And this, right here, is the massive shift, the fundamental revolution of quantum cryptography. For centuries, our security has relied on math problems being really, really hard to solve. But hard can become easy with a faster computer down the line. This method relies on the laws of physics being true. You can't just build a better computer to break the law of observation. An eavesdropper isn't just likely to get caught, getting caught is a physical certainty. This kind of technology gives us the power to create truly unbreakable secrets. And that forces us to ask a really profound question. When we can guarantee, really guarantee, that no one is listening, what kind of conversations are we going to start having? And which ones are we going to be afraid of?